All right, hello Calculus 3 students. Wanted to dive into the next section with you. We're going to talk a little bit about applications of double integrals. So I wanted to start off with something we've already discussed. So let's just say, recall, we've seen that the volume under a surface given by z equals f of xy and above a region R here is in the xy plane. So the volume under a surface f of xy and above a region R is, well, v equals the double integral over R of the top function f of xy dA. So we've already talked about this. Double integrals, you can interpret them in terms of volume, particularly when the surface f is above the region R, then it's exactly volume, right? If it dips below, then you're talking about positive volume and negative volume, just like we did negative area back in Calc 1. So that's the first thing that I wanted to look at. The second thing, though, is we haven't talked about this, but if you want to find the volume between two surfaces, what if you have one surface on top and one surface on the bottom? How do you find the volume between them? So let's go ahead and say that. So the volume, whoops, I can't spell volume today. The volume between two surfaces is, well, how does it work? It's the double integral, and you take the top surface. I'm going to say, let's just write it like this: top surface, the equation of the top surface minus the bottom surface, and then of course we're going to go dA. Let's say we're integrating over R. What is R? R is the projection of the two surfaces down into the xy plane. It's the region that the surfaces lie over. So let's see this using an example. So here we go. So example, let's simply find the volume bounded by z equals x squared plus y squared and z equals 2 minus x squared minus y squared. So I'd like to ask you to pause the video and try to sketch a picture of these two surfaces. Make sure that you're comfortable with that, and then come back and we'll keep going. All right, so let's see what's going on. So I'm going to try to draw my axes here, something like this. This is my x-axis, my y-axis, my z-axis. The first surface, this one, is just a paraboloid opening up. Let's do that one in red. So that's opening up like this. I'm not going to draw the boundary curve on the lip of it just yet. The second surface, this guy, is a paraboloid shifted up 2 and then opening down. So we'll do that one in green. So it's going 1, 2, and it's opening down like this. And so the point is, this solid that we're looking for is this interesting region between those two. Okay, so you've got a picture of the solid. Now we want to think about the area, the region in the xy plane that we want to set up our double integral over. And so what you do is you just imagine what the shadow of those two surfaces looks like in the xy plane. And you can actually see it's going to be circular. Let's see how we can solve for it precisely. All you do is you actually set those surfaces equal to each other. So I'm going to set x squared plus y squared equals to 2 minus x squared minus y squared. Pull everything across, and I get 2x squared plus 2y squared is 2. So x squared plus y squared is 1. So that's our R. This is our region of integration. And in fact, that means that this little region in the xy plane that we graphed is actually just the unit circle. And that's the region that the intersection of these two surfaces forms, and the solid between them lies above that region. So now we're ready to find the volume. So here we go. So the volume that we want is going to be the double integral over R of the top surface. In this one, it's clear the top surface is the parabola opening down, so 2 minus x squared minus y squared. Top surface minus the bottom surface, x squared plus y squared dA. I'm integrating over a circular region, so that sort of suggests that I might think about polar, and that's exactly what I'm going to do. So for the bounds, capturing our region R in terms of polar is really easy. R goes from 0 to 1, theta goes from 0 to 2 pi, no problems there. And then when I want to plug in, I know that x squared plus y squared is just r squared, so I get a 2 minus r squared minus an r squared. So this is just 2 minus 2r squared times r dr d theta. Let's push that r through, and so I get 0 to 2 pi, 0 to 1, 2r minus 2r cubed dr d theta. There's no thetas in the integrand, so I'm just going to go ahead and do that one separately. Actually, when I integrate 0 to 2 pi d theta, I just kick out a 2 pi. So there's 2 pi times the integral 0 to 1 of 2r minus 2r cubed dr. That's a calculus 1 level integral. Let's think about it. We're going to get r squared minus a half r to the fourth. 0 to 1 is going to be 1 minus a half is going to be a half. So this is just 2 pi times a half, which is pi. If that was too fast for you, that's the beauty of the videos. You can just slow down and pause it and work it out yourself. So that's the volume. The volume bounded between these two surfaces is pi. And the key formula that you want to be aware of is that you set it up as the double integral of the top surface minus the bottom surface, and you set up your double integral over the appropriate region, the region that the solid lies over. So I'll stop this particular video and pick it up